Okay, let's do part 2 of this video. So this is part 2. You should have already watched the part and seen example that I talked about area between two curves and examples 1, 2, and 3. Okay, so here's another way these questions could be asked. Okay, if you look at example 4 here, oops, sorry. There we go. Now it's okay. You can see, and then I give you the graph again here. Right? The difference between this and example 3. In example 3, I told you what the bounds were. This one doesn't tell you what the bounds are. Okay, it's not given. So, but it does say find the area of the region between the two curves. So it wants what's in between these two right here. So we need to find these intersections. Okay. Sometimes there's a graph given for you. You can see where the x values are going to be. You can see the x values are 0 and 4. Sometimes it's not going to be given for you, and you have to figure that out. Here's how you figure it out. Just set the two equations equal to each other. Right? Multiply by 4. I'm going to move this over. Factor. And then I can see that 0 and 4 are my x values. Do I need my y values? No, I don't. The reason I don't need my y values are, remember, right? Here's my rectangle I'm going to be dealing with right here. Okay? The width of the rectangle is dx. That's what I'm integrating in terms of. Since I'm integrating in terms of dx, I need these to be x bounds, 0 and 4. I don't need the y values. The y values are the change in the y right here, the upper minus the lower. So which one's the upper one? Oh, it's y equals x. Which one's the lower one? X squared over 4. Okay, there's my integral. Okay, so in this one, the difference with this type of problem is if the bounds aren't given to you. In example 1, 2, and 3, the bounds were given to you. All right, in example 4 here, not given to us. Okay, we integrate. We take the antiderivative. Okay. Evaluate from 4 to 0. Plug in 4, so that's going to give me 16. That's going to give me 8. 64 over 12. And that's going to reduce because the 4 goes away. So that's going to give me 16 over 3. You can plug in the lower bound. And that's going to be 0 because it's a polynomial. So I have 8 minus 16 thirds, or 24 thirds minus 16 thirds. So it's 8 thirds there as my area. Okay, and that seems reasonable. If I look at it right here, this whole thing is an area of 16. It's 4 by 4, right? And so it looks like, and actually I can even look at the triangle there. This triangle has an area, it's a base and height of 4 and 4. So that's going to have an area of 8. Right, and so this seems like a third of that seems pretty reasonable there. Right. Okay, so we have 8 thirds there. Okay, so if this is another of the same type, right? So complete that example, right? Check against what I have online, and then ask me questions if you have it. I'm going to skip to example 5 here. Find the area of the region bounded by the two curves. So we have this, right? Okay. Now we don't know where all the, actually, can we tell the intersections? Oh, it looks like we can. You can see that the intersections are at -3, -1, and 3. So it's kind of nice. Now, by the way, if we didn't know where the intersections are, that's easy to find. Or it can be easy to find depending on the equation. You set them equal, right? So to find intersections, okay? Let's say you can't really see it on the graph. This is just how you would find the intersections. You set the two equations equal to each other. Right? I just basically set this is equal to y, that's equal to y, so they're equal to each other. Okay? I'm going to okay. This equals 0. Okay? And I think now I need to factor it. And the technique I'm going to use to factor this, I'm going to use the factor by grouping. So I factor out an x squared there. And I factor out -9 there. And then I can take out the x plus 1. So factor by grouping back from Algebra 1 days. Okay, gives us our 3 x values of -1, 3, and negative 1. Okay, so those are our 3 intersection points that we'd have for ourselves. Why do we have to find those intersection points for ourselves? We have to find them because we don't know what the upper bound and the lower bound are going to be. Okay, so if we look at this, let's look at, here's my rectangle. Region A, there's my rectangle. Region B, here's my rectangle. Okay, so for region A, okay, I can see that x cubed minus 9x, it was labeled for us, that's the larger one. So for this one, the upper minus the lower, for this guy right here would be the x cubed minus 9x minus the 9 minus x squared. Okay, so that's the integral I'll use. It's from negative 3 to negative 1. Okay. If now for this next region between negative 1 and 3, which one's the upper bound? Oh, for this one, notice that 9 minus x squared is the upper bound. That's the one that's on top. So it can change if there's multiple regions. It can change which one's on top. So that's why it's so important to know what your graph looks like. Okay, so we'll do 9 minus x squared is the top one, minus the x cubed minus 9x. Okay, so when I subtract them, I'm going to have 9 minus x squared minus an x cubed plus 9x. If you'd like to put it in standard form for yourself, go right ahead. No need to. You'll see that these two are really the same expression, here, but the opposite signs. Okay. Okay, and we talked before when we have the same expression but opposite signs, it might be helpful before you actually do your antiderivatives to what I'm going to do here is I'm going to basically take out the negative by flipping my bounds. For myself. Okay, and so that one is ready to go. Okay, I do the antiderivative. Okay. And because I changed these and had them look exactly the same, the antiderivatives are going to be exactly the same. And that was one of those advantages. Okay, so at this point, I can plug in my values, right? So I'm going to plug in the negative 1, so it's going to give me, I'm going to go all the way over here because it looks like I'm going to need the space. So it's going to be 1/4 minus 1/3 minus 9/2 plus 9 minus the lower bound, which is 81/4. Plug that in, so it's going to give me minus, let's see, negative 9 because it's going to cancel. And then this is going to give me minus 81/2 and then plus 27. Okay, I'm going to just keep going and plug all these in. So I'm going to plug in that negative 1 again, the upper bound. And then I'll subtract the lower bound there. Plug that in, 9. Okay, so I have all those. Okay, now one of the reasons to just write this whole thing out is now I can actually go and start to work with some of these, like see all the fourths here, right? They're going to really do a nice job of canceling each other out for myself. Okay, so 1/4 minus 81/4 is negative 80/4, so that's negative 20. And then, oh look, I have this, and that's negative 20 again. That's negative 81, negative 80/4, or negative 20 again. So another minus 20. Okay. Okay. Myself. Okay. Hey, look at this 27. I have a minus 27 right here. and I have a plus 27 there. So those are going to cancel. So I'll cancel those out for myself. Okay. Excuse me. Okay, so then I go through and I just keep looking at this and kind of combining what I can here to get my answer. If you want to, you can distribute this negative here so that you don't have to deal with that. Maybe I'll do the same thing here. Okay, for yourself. All right, and you put together. So I'm going to put all the halves together next. So I have negative 9 halves plus 81 halves. So that's going to be 72 halves. That's 36. Okay. Let's see. Negative 9 halves. There's another 36. Okay. Notice I'm crossing out as I do it. Oh, look at this plus 9 and this minus 9 cancel. That plus 9 and that plus 9 make it another 18 there. Okay, for me. And then I have thirds, so I have negative a third minus 2 thirds, so minus another third, so that's minus 2 thirds. Okay, so you can see that I kind of put some things together selectively. I'm sorry I'm running out of space here, but that's 72 minus 40 is 32, 50, so it would be 49 and a third when it's all said and done. All right, putting those together there. Okay, lots of numbers on that type of problem for yourself. Okay.